So let's try this example. Example 1a. We are going to find the rate of change of f at the point P in the direction from P to Q, given that f of xy is equal to x times e to the power xy, and then b, in what direction does f has the maximum rate of change? Find the maximum rate of change. So we are going to solve this example a and b. Let's start off with a. Now we are asked to find the rate of change of f, which means that we want to find the directional derivative. Now from the previous lesson, we got to understand that the directional derivative of a function, here we have a function of two variables, x and y, so that is basically equal to the dot product of the gradient function and the unit vector. So we need to find these two components so that we can obtain the dot product of these two vectors to find the directional derivative. So first of all, we have the function f of xy, and that is equal to x times e to the power xy. So we have fx, the partial derivative of this function with respect to x. Now these two are all functions of x, so we can basically split them. We can have x on its own and then e to the power xy on its own, meaning that we are going to use the product rule. So we hold x, we differentiate e to the power xy with respect to x. Now we differentiate this x on top, and then we have 1 times y is y. Therefore we are going to drop down y, and then we have e to the power xy, plus we hold e to the power xy, and then we multiply that by the derivative of x, which is 1. Therefore we have fx to be equal to xy e to the power xy plus e to the power xy. Now we have e to the power xy, e to the power xy, so we can factor out e to the power xy, so that we have in the bracket xy plus 1. So that is fx, and then for fy, x is going to be a constant, so that is x. We differentiate this with respect to y, so we differentiate y, we have 1 times x is x. We drop down x, we have e to the power xy. So basically this becomes x squared times e to the power xy. So x squared times e to the power xy. So that is fy. Next we have the gradient of the function to be equal to the vector, which has components fx e to the power xy times xy plus 1, comma fy x squared times e to the power xy. Now the next thing is we are going to find the gradient of the function at the point P, which is 2, 0. So we have gradient of the function at the point 2, 0 to be equal to, so let's say for fx we are going to have this to be e to the power 2 times 0, x is 2, y is 0, all times 2 times 0 plus 1, and this becomes, let's say, e to the power 0 times 0 plus 1. Now any non-zero number raised to the power 0 is equal to 1, so this is 1 times 1, and that is equal to 1. So we have this part, this component, going to 1, so that is equal to 1, comma, and then for this we have x to be 2, so 2 squared times e to the power 2 times 0. E to the power 0 is 1 times 4 is 4, so that becomes 1, 4. So this is the gradient of the function at the point 2, 0. So next we want to find the direction vector. Notice that in this question we are not given the direction vector, however we are given 2 points where we need to find the direction vector, that is from P to Q. So we have the direction vector pq, and that is equal to q minus p, and thus we have the point q to be 0.52. So for the x component, we have 0.5 minus that of p is 2, that of p is 2, comma, the y component, we have 2 minus 0, and that becomes negative 1.52. So this is the direction vector. This is the direction vector. So we are going to let the unit vector be u cap. Therefore, we have the unit vector u cap to be equal to the direction vector divided by its magnitude. So this becomes negative 1.52, all divided by the square root of, this becomes 2.25 plus 4. Negative 1.5 square becomes 2.25. So this finally becomes negative 1.52 all divided by the square root of 6.25, and that is equal to 2.5. So we are going to have negative 3 over 5, 4 over 5. So that is the unit vector u cap. Therefore, now the directional derivative of the function at the point 2, 0 is equal to the dot product of the gradient of the function at the point 2, 0 and the unit vector and next what we are going to do is we are going to multiply corresponding components and we add them up. So 1 times negative 3 over 5, that is negative 3 over 5, plus 4 times 4 here is 16 divided by 5. We have common denominator, so we are going to add the values at the numerator. So negative 3 plus 16, that is 13. Therefore, we have the directional derivative of the function at the point 2, 0 to be equal to 13 divided by 5. So that is for A. B, in what direction does f has the maximum rate of change? And we are asked to find the maximum rate of change. Now, at this point, we understand that the directional derivative of a function is equal to the dot product of the gradient function and the unit vector. Now, the expression on the right hand side can as well be expressed as the magnitude of the gradient function times the magnitude of the unit vector times cosine of the angle theta, where theta is the angle formed between these two vectors. Now, because we are interested where the function increases most rapidly, we want to find the maximum value of cos theta. Now, the maximum value of cos theta is equal to 1, and that occurs when theta is equal to 0. So when theta is equal to 0, you have cos 0 to be equal to 1. That is the maximum value of cos theta. So that becomes the magnitude of the gradient function times the magnitude of the unit vector. Now, the unit vector is a vector which has magnitude of 1. And so if you have gradient function or the magnitude of the gradient function times the unit vector, which is 1, then it means that the maximum directional derivative is equal to the magnitude of the gradient vector. So this is what we need. Now, we are asked that in what direction does f has the maximum rate of change? Now, f experiences the maximum rate of change if f is in the direction of the gradient vector, or better still, if the unit vector has the same direction of the gradient vector. And then to find the maximum rate of change, that is given by this formula. Therefore, the maximum rate of change, which is the maximum value of the directional derivative, is equal to the magnitude of the gradient vector. So let's find that. So we have duf max, and that is equal to the magnitude of the gradient of the function at the point 2, 0. So that is given by the vector 1, 4. And to find the magnitude, that is equal to the square root of 1 square plus 4 square, and that is equal to 1 plus 16. And therefore we have the square root of 17. So that is the maximum value of the directional derivative, square root of 17. So similarly, the minimum value of the directional derivative is given by negative of the magnitude of the gradient vector. Now this is obtained when theta is equal to pi, or 180 degrees. Now when theta is equal to 180, cos 180 is equal to -1. So that is how come we have negative attached to this. And this also happens when the unit vector u cap is oppositely directed to the gradient function. Now let's move on as we solve the second example. So for example 2, if the temperature at a point in space is given by this function, in what direction does the temperature increases fastest at the point 1, 1, -2, and then what is the maximum rate of change? Now from the previous example, we can conclude that the temperature increases fastest in the direction of the gradient vector. We got to understand that the function experiences the greatest increase if the function is in the direction of the gradient vector. So in this case, the temperature increases fastest in the direction of the gradient vector. Now, to find the maximum rate of increase, we know that the maximum directional derivative is equal to the magnitude of the gradient function. So let's try to find the gradient function, and then we evaluate its magnitude. So we have the function t of x, y, z, and that is giving us 80 divided by 1 plus x square plus 2y square plus 3z square. Now to find fx, we are going to use what we call the quotient rule. So given that y is equal to u over v, so assuming you want to find dy dx, that is simply v du dx minus u dv dx, or divided by v square. So we are going to first of all consider the numerator, this to be u and then that to be v. So then we have 1 plus x square plus 2y square plus 3z square times du dx. When you differentiate 80, you have 0 because it's a constant, minus 80, that is u, and then times dv dx. So you are going to differentiate the denominator with respect to x. So this is a constant, it goes to 0, this also goes to 0, this also goes to 0. We differentiate this, we have 2x. Okay, we have 2x, and we have this all divided by 1 plus x square plus 2y square plus 3z square, and then all square. So finally we have fx to be equal to, so this part goes to 0. We have negative 160x divided by 1 plus x square plus 2y square plus 3z square all square. So for the next one, that is fy, we don't need to go through the whole of this process. Now we know that whenever you differentiate 80, we are going to get a 0. So what we are going to do is we are going to select, first of all we are going to have this negative here, because looking at the original formula we have a negative here. So negative, and then we have our 80 here, and we are going to differentiate this, the denominator, this time with respect to y. So we have 4y, we are going to have 4y. So we have 4y like this. So 4 times negative 80 is negative 320. So that becomes negative 320y. So negative 320y, all divided by the same thing, 1 plus x square plus 2y square plus 3z square all square. And then for fz, so we differentiate this, we have 6z. So 6 times 80, that is 480. So we have negative 480z all divided by 1 plus x square plus 2y square plus 3z square all square. Then we have the gradient of the function xyz to be equal to, we are going to have negative 160x, negative 320x, negative 320y, and then negative 480z, all divided by 1 plus x square plus 2y square plus 3z square all square. The next thing is we need to find the gradient of the function at the set point, which is 1, 1, negative 2. So that is equal to, we have negative 160 times 1, that becomes negative 160. Negative 320 times 1, that is still negative 320. And then negative 480 times negative 2 becomes positive 960, all divided by 1 plus, this becomes 1 square, which is 1, plus y square. So 1 square is 1, 1 times 2 is 2, plus z square. So negative 2 square is 4, 4 times 3 is 12. And then we have this all square. So this is 1 plus 1 plus 2, which is 4, plus 12 is 16. So 16 square. Let's evaluate 16 square, and that is 256. So we have this to be equal to 160 divided by 256, that is simply 5/8. So negative 5/8. And then this 320 divided by 256, that is also 5/4. So negative 5/4. 960 divided by 256, and that is also 15/4. So that is 15/4. Now let's continue. Since we want to find the maximum rate of increase, then we are going back to the maximum value of the directional derivative. So dut of 1, 1, negative 2, that is the maximum value, is equal to, now we are going to take the magnitude of this. Okay, so we are going to have the square root of the square of each of the components, and then we are going to add them up. So negative 5 over 8 square plus negative 5 over 4 square plus 15 over 4. So that is equal to, we have the square root of negative 5 square, that is 25 over 8 square is 64, plus negative 5 square, 25 over 4 square, 16, plus 15 square is 225, 4 square is 16. And then we go further, we have the square roots of, now the LCM is 64. 64 divided by 64 is 1 times 25, 25, plus 64 divided by 16 is 4 times 25 is 100. 64 divided by 16 is 4 times 225 is 900. So when you add everything on top, then you have 1025 divided by 64, and that is equal to 5 over 8 times the square root of 41. Notice that temperature is measured in degrees Celsius, and we have XYZ measured in meters. Therefore, we have the maximum rate of increase, to be equal to 5 over 8 times the square root of 41.